Okay. Hello, everyone. Thanks for the invitation, Diego and Raffaele. So today I will be giving you a short overview of ultralight dark matter and their experimental searches. So I'll be telling you about the various dark matter candidates we are interested in that is in the ultralight region, and then I will highlight some of the new recent experimental results. Okay. So let's start with mass and couplings of the particle. So the mass range that I will mostly cover, like in this overview, is going to be between somewhere 10 to minus 22 eV, where if you are lighter than this mass, you are going to significantly impact galaxy formation and hence excluded. On the other side, you have order EV, where and this range is somewhat fuzzy, but it is where roughly where the occupation number of the dark matter particle becomes order 1, and at which point, whether you think about it as a wave or as a particle depends on your experimental setup. And experiments based on thinking of it as wave and as a particle will have competing sensitivities, as I will show you later. Okay. So apart from the mass, we also look at the couplings. So the particles that we are interested in can be a pseudoscalar, can be a spin-1 particle, a vector, or a scalar. So these are axions, dark photons, and the dilitons. So these particles can have different couplings to the standard model. For example, to the standard model photon, the standard model fermions, especially the electron. And for particular dark matter models like the QCD axions, there can be additional couplings like the EDM coupling, which is discussed in the Mina's talk at the workshop. Okay. So these particles can be produced easily in the early universe through non-thermally produced. So there are two types of production mechanism, either pre-inflation or post-inflation. So the pre-inflation or during inflation productions can be basically either the misalignment mechanism, which works for scalars and pseudoscalars, and usually favors light mass particle, or the inflationary production for the vector dark matter, and this usually works for dark photon masses that is above 10 to the minus 5 eV. Okay, so those two are relatively well understood, and there are some new progress in the understanding of post-inflationary production by different type of topological defects like strings and domain walls, especially for the QCD axion. And you probably have heard interesting talks by Josh Foster and Marco Gorgetto at the workshop in their progresses. Okay, so now we know the particles that we are interested in, how they are produced. Now let's see let's try to design experiment. And first we need to understand like what we are competing against, right? So the competition can be generally separated into two categories, radiation and force, okay? So, and most of the radiation comes from stellar cooling. The sun in particular is a very good object at producing these light particles in huge abundance, and the stellar cooling bond and the subsequent search for these particles that are produced by the sun, by CAS or by xenon, has placed very strong constraints on the existence of these particles, even if they are not dark matter. So recently, there are some very exciting development of what is known as the stellar basing, pioneered by Ken van Tilburg, where he outlined how these particles, if they are produced non-relativistically, can be gravitationally trapped and built up in number, and which have very interesting experimental consequences. I will refer you to his talk at the GGI for more details. So the second competition we have are forces, and these can be fifth force constraints or EP violation tests. And usually, like when you have a particle which are coupled non-derivatively, then these constraints are much stronger than the constraints you get from radiation. And apart from very limited cases, we do not know how to go beyond these constraints. Okay, so somewhat related to the fifth force and the EP violation limits, the force limits are what is known as the density effect, which is basically the idea that the presence of the central matter can significantly affect the dark matter properties, either making them unobservable or like the dark matter will back react on the standard model matter, leading to effects that tells you like these parameter space are excluded. Okay, so this is similar to the plasma effect for the photon when you consider photon interacting with a metal or like a plasma. And this limit further tells you that it is very hard to look for particles which couples non-derivatively. Okay, so apart from these two main competition, you also get competition in certain mass ranges from black hole superradiance, as well as cosmology. But today I will be focusing on lab tests, so I will not go into details about those. Okay, so to summarize, this is the table again, and for most of these couplings, which are non-derivative couplings, you have both the stellar cooling and the fifth force constraints, while for these three couplings, the axion photon coupling, the kinetic mixing of dark photon, as well as the axion wind coupling, because they are derivative coupled, you are only subject to the cooling down. So in the following, I will take this as an example and discuss some of the experimental progresses in looking for axion. Okay, so let's go to the lab. So it's safe to say that most of the experimental result has been coming in this energy or mass range that is around micro EV or radio frequencies. This is the most well-motivated parameter range for QCD axion dark matter, and the ADMX experiment is the first to go through the QCD axion band. So this range, which is most best theoretically motivated, is also the range that is in some sense easiest to look for, because both the energy that we are looking at, which is equal to the dark matter mass being a gigahertz, as well as the size of the object that you want to build to match the dark matter Compton wavelength, which is order a meter, are within the size and the energy range where existing technologies are very developed. Okay, so because of this, there are a lot of cavity experiments which spanning like two order magnitude in parameter space, placing very exciting result, interesting limit, and have very exciting reach. Okay, so the progress in the last 10-ish years has been people trying to expand the reach for axions and the dark photons to either the higher or lower masses. And to discuss how we are motivated to build this experiments, let me introduce you to this simple equation. Okay, so which characterize how well we can build experiment to look for these dark matter candidates. Okay, so here epsilon squared is characterize the coupling between the standard model and dark matter. For dark photon, this is basically the kinetic mixing parameter, and for axion, it is this combination of the axion photon coupling, the magnetic field, and the axion bonds. Okay, so raw dark matter is the local dark matter density. The volume is your target volume, and the time here is the total integration time that you want to take. Okay, so this combination of the parameter equal to 1 is the best you can do, given with a classical experiment to look for dark matter coupling with this parameter. Okay, so and this equation basically assumes that you take all of the energy that is available to you in the visible component of the dark matter, and convert it all into a signal that you can detect with 100% efficiency. Okay. So if we put in some reasonable numbers, like a 10 Tesla magnetic field, volume of meter cubed, and the integration time of a few years, it suggests that we can use these type of devices to look for QCD axion with the QCD axion photon coupling. Okay, so how do we do this? So towards the lower mass end or lower lighter masses or lower energies, the idea is to build an LC circuit, and this is the scheme that is adopted by DM Radio and also the abracadabra experiment, where they try to build an LC circuit with a resonance frequency that matches the mass, and of course a size of a detector much smaller than the Compton wavelengths of the axion. Okay, so there's a lot of experimental progress. In particular, I want to highlight this result from the abracadabra prototype, where they are becoming competitive to the solar cooling bound, stellar cooling bounds, and the cost constraints. So there are also ideas to go to higher frequencies, and these are what is known as the dielectric haloscopes. First, I think like pioneered by the IDMS collaboration, and then like also adopted by the Manimax and the Lampos collaboration, where we try to build detectors, again, has build metamaterials, again, have a resonance mode, which has a frequency that is comparable to the axion mass. But now we want to build a detector that is bigger in size compared to the Compton wavelengths of the particle. And using these metamaterials, we can get access, basically in some way like align a lot of cavities together, and that allows us to use a large volume detector, much larger than the Compton wavelengths of the particle, to look for the axion in that mass range. Okay, so there are also some new experimental results coming from the Lampos collaboration, where we get into unexplored parameter space for dark photon, dark matter. Okay. So I think it's safe to say that we are getting towards this ultimate limit of classical experiments of epsilon squared rho VT equal to 1 in a wide range of parameter spaces, and a lot of experimental progress is on the way, which allows us to look for these particles in parameter spaces that are never explored before. Before I move on, I want to also highlight the recent result coming from the sensory collaboration, where they use a skipper CCD to place a very strong limit, well, beyond like the stellar cooling bound in the range of 3 or 4 eV to 10 eV. Okay, so the reason I want to do this is because I want to like emphasize that this mass range of 1 to 10 eV is the region where either you think about the dark matter as a wave, and as a result you design like interference devices to look for energy deposition of these dark photons, or you think of it as just a particle and look for its effects in ionization of electron hole pairs, gives you a similar experimental limit. Okay, and the reach are also relatively comparable. Okay, so that's mostly about the existing experimental program, and trying to reach the equation of like a epsilon squared rho VT equal to 1. There are also many ideas which allow us to go beyond, and these ideas can be divided into mainly two categories. The first category of ideas involve putting the detector not in vacuum. So the idea is that if you preload the detector with some energy or like a lot of power in a frequency omega, and tries to look for the dark matter induced signal at a frequency that is close to omega, then in certain setups, you can gain this ratio of the frequency which you are looking at over the frequency where like the dark matter is oscillating. So for example, in the case of atomic clocks, this frequency is an optical photon, so it's like EV, while the dark matter can be oscillating at a frequency that is of order like hertz, or even like 10 to the minus 7 hertz. So this is a ratio that can be easily like 10 to the 10 or 10 to the 20, and and be a very important enhancement for the experimental reach. Okay, so there is a new experimental design, a more explicit experimental design, realizing this idea by both the Slack group and also independently by Robert Lazenby at Stanford, where they try to build superconducting cavities and look for axion-induced transitions from one mode to the other. There is a talk by Sebastian Ellis at the workshop, which uses similar ideas to look for gravitational wave, and I encourage you to take a look. So the second type of ideas people have to go beyond this, the limit, the epsilon square rho VT equals 1, is to beat down the quantum noise. And the idea to do that is outlined by the haystack collaboration, basically using the technique of photon counting. Okay, so it is very easy to realize in optical frequencies, but I want to highlight this recent result from the Chicago Fermilab group, where they managed to do photon counting in the radio frequency. So this is their setup. They combine a qubit and a fluid cavity. You can see like the device is very, very small, but nevertheless, they get a sensitivity, at least in depth, comparable to the ADMX for the photon dark matter parameter space. And I think this result is very exciting, and we'll see how much we can take this device and make it a tunable experiment, which can cover a much wider range of parameter space. Okay, so that's most of the things I want to cover. I want to end with some questions that I found the most exciting. So the first, again, being like, how do we go beyond this limit? And then also, if we can build single photon detectors, in particular in the terahertz energy range. And I want to highlight some of the recent improvement of our understanding of the background led by the Stuni group, Ruven, Isig, and his collaborators, like Daniel and Peiji, who I think are in the audience, where they understand a new source of background, which will probably significantly impact how we design experiment to look for dark matter in this range, especially like the EV mass range. Okay, so I will end with a shameless advertisement for a school that we are organizing at PI, where we try to bring in experimentalists and theorists to teach each other about what is interesting and exciting in their own field, and try to build together some new experiments that can further our searches for dark matter in the ultralight and also maybe light sub-GeV mass range. And it will be hopefully happening in September 2022. And we welcome you to send your students, postdoc, and maybe yourself too. Thank you very much. That's all I want to say.
Thank you.
Thanks, Curly. This is Jeff. Just a quick question. I'm a little confused about this in the sense that do these experiments ever plan on reaching such a threshold? I mean, I thought ADMX, these different experiments are always going to be having significant backgrounds, and they don't really ever plan to get to this sort of threshold. So in what sense is this an interesting target, and will they ever be reaching it?
I didn't hear like off like what you said.
Sorry, maybe I'll just repeat it again.
You are asking about this equation, like
Yeah, my question exactly is that. So, I mean, is this relationship ever really a target for an experiment in the sense that I thought ADMX and other collaborations always have a significant backgrounds that they have in their experiment, And
Yeah.
I didn't appreciate, at least, that they were ever going to be reaching this sort of threshold.
I
Is the
think like
target they're going to be reaching
actually,
in the future, or kind of where is it going to go? Are they already ever
I think
there?
like ADMX is actually very close to this limit.
I see. Okay, I just didn't really appreciate that
Yeah,
point.
yeah, yeah.
So the different experiments that are running right now are kind of, and ADMX included, are targeting this sort of range.
I think like this is the ultimate like a target for this experiments. Usually like you are going to be like 1 or 2 magnitude off, but like if you are only like 1 or 2 magnitude off, you get very close to the QCD axion line.
I see. Thanks.
Yeah.
We can have
ADMX
another-
is really, really close. Like you can check out like these papers I should have mentioned. These 2 papers like where they discuss like what are the ultimate sensitivities for like experiments like DM radio and also ADMX. And ADMX is really running at a point which is in some sense hard to improve because it is just so great. Yeah.
No, also the target depends on the coupling. I mean, for some higher masses is not correspond to a tiny noise. I mean, it's not necessarily that you have to go beyond quantum limited. It depends what coupling you're looking at.
Yeah. So here, like the coupling that I'm setting as a target is really the QCD axion line. Then like it's independent of the mass because it's always this combination that show up.
Another couple of questions. Then we have like also a discussion session. So keep some question for the discussion.
Hi, Curly. This is David. Thanks for the nice talk. So you mentioned, or you flashed single photon terahertz detectors, which I understand are important for some of these detectors. But what's the status of this technology? Do you have any bird's eye view? Like, is that 10 years away? Is it still kind of sci-fi? Because there's a whole bunch of things I could imagine doing if I could detect gigahertz to terahertz photons one by one.
I don't know. I don't know. I think like we will need like experimentalists to show us what we can do. Right now, like yeah, it's a question because like I have no answer.
Okay, no worries. Thanks.
Yep.
All right. So thank you very much, Curly. Again, if you can stay for the discussion, I'm sure there will be more questions, but I mean, to avoid conflict with the other speaker schedule, we're moving on for the moment.
Sounds good. Yep.
Thanks.